We're going to go through the AS Unit 1 paper from CCEA, and this is Physics Unit 1 from June 2015. Question 1a, state the principle of conservation of energy. So this is the statement that you learn off from your notes, that energy can neither be created nor destroyed, simply converted from one form to another. Question B asks us to define power, and power, remember, is work done divided by time taken. So you could describe it as the rate at which work is being done, or the rate of doing work, or you could literally just say power is the work done divided by the time taken. Okay, part C then is asking us to look at this tidal barrage. A tidal barrage uses the ebb and flow of the tides to produce electrical energy. The moving water drives a turbine and ultimately electrical energy is generated. So you can see we have two levels of water here, high water, low water. And the result of that is that the high water makes its way down with its gravitational potential, pushes itself through the turbine out to the lower level. And that's how we're producing the energy. So we're told that it comes down through a vertical height here, and we're interested in the mass of water, the minimum mass of water moving through the turbine every second if the electrical power output from the barrage is 30 megawatts, assuming no energy losses. So if power is the energy converted over the time taken, and the energy converted in this case is gravitational potential, and we're dividing by the time, then this is our expression. We're interested in that mass with a t value of 1. So rearranging this, the mass is going to be power times time over gh. So t, remember, is just 1 second. G we can get from our formula sheet. Power and h are given in the question. So top line we've got 30 mega times 1 second, and bottom line we've got 9.81 times the 6 meters. And I'm getting for that approximately 510,000 kilograms. And they've asked us to be accurate to two significant figures, so that's the appropriate rounding up there. Question 2. A new sports car is to be tested on a long, straight, horizontal test track. The test driver starts the vehicle from rest and accelerates uniformly to a maximum velocity of 200 kilometers per hour in 12 seconds. The car continues at this velocity for 20 seconds before the brakes are applied, causing constant rapid deceleration. The car comes to rest in a further 8 seconds. Show that 200 kilometers per hour is equivalent to 55.6 meters per second. So all you do in a case like this is you convert 200 kilometers to meters, and you convert 1 hour into seconds and divide those numbers, and you'll get what you're looking for. So 200 kilometers per hour is a speed that would be calculated by dividing 200 kilometers by 1 hour. So it would also be the speed for 200,000 meters divided by 3,600 seconds. So 200,000 meters is 200 kilometers, 3,600 seconds is the number of seconds in 1 hour. And we divide those, we'll get meters per second. And that is the value we were looking for. Part 2 then. Sketch a velocity time graph to represent the motion of the car on the track. Include relevant numerical data on both axes. So this kind of sketch involves looking at the important values, like for example the 56 or 55.6 meters per second that it reaches. So that'll be a vertical important number. Horizontal important numbers would be 0 at the beginning, 12 seconds by the time it reaches this maximum velocity, continuing at that for another 20 seconds, and then going back to 0 during the remaining 8 seconds. So we've got 0, 12, add 20 to get 32, and then 32 plus 8 takes us up to 40 seconds. So we need to mark those times out on the graph, and we need 56 on the vertical scale. So we go from 0 up to 56, travel at that for a while, back down to 0. So we need to put that information onto this graph. So we're interested in obviously marking out 0 here, and we need to go to 40 seconds. So I would put 40 there. So we've got 10, 20, 30 and 40. And then we need to go to 55.6 on the vertical scale. So I would go 20, 40, 60 on the vertical axis. That will include our 55.6 value that we're looking for. So we have a point here at 0, 0, a point here at 12 seconds when it reaches 55.6. That continues on until 32 seconds, and then the last 8 seconds is going back to 0. So we get a slope up like this, another one like this, and one coming down like that. 12 seconds of accelerating, 20 seconds at a steady speed, and 8 seconds to decelerate. You probably also want to put the exact numbers of these positions of change onto the axis as well, just in case there are marks for that, like so. Next part asks us to use the graph to find the total distance the car has travelled, and that's going to be the area under this graph. So you can break it into 2 triangles and a rectangle, or you can think of it as a trapezium, but basically you need to find the area and record that then as the distance travelled. And so that's going to come to the area of the first triangle, a half times the base times the height, the area of the rectangle, which is the base times the height, and the area of the final triangle, which is half times the base times the height. Add all those up then, and that comes out to be 1668 meters. Part B1, state Newton's second law of motion. Remember, Newton's law is F equals ma, so what we need to remember is that the F there is the resultant force. And so we can say that the acceleration of an object is proportional to the applied resultant force and inversely proportional to the mass of the object. The mass of a sports car and driver is 1480 kilograms. It is now driven along an upward sloping track inclined at 12 degrees to the horizontal. The driving force Fd from the engine is 8 kilonewtons, and the car accelerates up the slope. The frictional force opposing the motion is 200 newtons, as shown in the figure 2.2. So we've got a driving force here of 8 kilonewtons, resistance force here of 200 newtons, and we've got an angle of 12 degrees. Calculate the acceleration of the car up the slope. So we just add to our diagram here that the mass of this object is 1480 kilograms. Because we're going up a slope, we also need to take account of the fact that this object will have a weight mg, and that a component of that weight will act along the slope. A component will act into the slope, and another component will act along the slope. So this is also going to be 12 degrees. So this component that we're interested here, which I'll emphasize in black, this is the one that participates in the interaction up the slope. And it's going to have a value of mg sine of 12 degrees. So the resultant force equals ma, and A will equal F over m. So we need a resultant force on the top line and the mass of 1480 on the bottom line. So we get 8,000, which is up the slope, minus 200 because it's down the slope, and minus 1480 g sine 12 degrees. Because these are both down the slope, this one's up the slope, so these both get a minus sign when we're adding all the forces together, and 1480 is the mass on the bottom line. And I'm getting a value of 3.23 meters per second squared. Part 3, a second heavier car is now tested alongside the sports car. Both cars start from rest at the start of the track and are travelling in the same direction up the slope. The acceleration of the second heavier car is 60% of that of the sports car. How long after the start of the test is the separation of the cars? 180 meters. Firstly, the relevant UVAST equation is S equals UT plus a half AT squared, but since both start from rest, you can ignore that term, and S just becomes a half AT squared. It's also worth recognizing that we've got two accelerations now. We've got the original acceleration, and we've got a second acceleration, which is 60% of the first one. So we can say the second acceleration, A2 here, is 0.6 of A1. So we can write an expression for the difference in S's, since S1 will equal a half A1 t squared and S2 will equal a half A2 t squared. Then S1 minus S2, which is the change, or the difference between them, the separation, is going to be the separation of those two expressions. So, difference between S1 and S2 is the expression for S1 minus the expression for S2. But we also know that A2 is 0.6 of A1. So we can also write it as a half A1 t squared minus a half of 0.6 A1 t squared. So we can fill this in now because we know everything except t. And we know from the first part that A1 is 3.23 meters per second squared. So we're looking for the time when this separation goes to 180. So 180 equals a half times A1 times t squared minus a half times A2, which is 0.6 of A1. Sorry, I shouldn't say 0.69, just 0.6 of A1, times t squared. Just eliminate that. And that's going to be 1.615 t squared minus 0.969 t squared, which gives you 0.646 t squared. So 180 over 0.646, the root of that is going to be t squared. So t will equal the root of 180 over 0.646. And that's giving me 16.7 seconds. Question 3. On the 14th of October 2012, skydiver Felix Baumgartner stepped out from a space capsule approximately 39,000 meters above the New Mexico desert in a successful attempt to break the record for the highest and longest free fall. It took him 10 minutes to fall to Earth, and he was in free fall for just under 5 minutes. Describe an experiment to determine the acceleration of free fall g in a school laboratory. Your account should include a label diagram, the data required and how the data is to be obtained, an explanation of how the data could be used to obtain a value for g, and how you would improve the reliability of your results. So you want to be able to draw probably something like a straight free fall experiment where you had an electronic timer and something to release it and start the timer, and something to stop the timer. And in school we still have the electromagnet, the old school electromagnet version, where when you press a button to drop a ball bearing from the electromagnet, it starts the timer. The electromagnet crashes through the little trap door, and that stops the timer. So, as I say, we've got an electromagnet. It starts the timer when you let go of this ball bearing. The ball bearing falls a distance s, which you would measure with your meter stick. It then crashes through this trapdoor and stops the timer. So you can vary the amount of s that you're measuring with your meter stick. The time for it to fall is measured on this timer, and you've got, similar to the last question, the idea of acceleration from rest. So you've got s equals a half at squared. You don't have to put ut in because it cancels out because u is 0. Say this term cancels and you end up with just s equals a half of gt squared. So we're measuring this and the time, and since it's proportional, since s is proportional to half g times t squared, you're going to want to plot s up the side, t squared along the bottom, and you'll get a straight line where the gradient here is equal to g over 2. And so you double your gradient to get the value for g. So you would need to learn this diagram from your notes. You need to be mentioning what you're trying to get. You're trying to get the time for a free fall and the height that the object fell, and you need to be talking about the instruments of how you're getting that data. So obviously meter stick for measuring the heights and the electronic timer for measuring the times. How the data could be used to get a value for g is all this stuff down here about the graph, and the fact that you've looked at this equation and you recognize that if you plot s versus t squared, you're going to get a value of half g for your gradient, and how you would improve the reliability of your result. So what you're going to do here is you're not going to take one reading for each fall, you're going to take times for multiple falls. You're going to ignore what appear to be anomalous results and take a mean of several times that seem reliable for each one of those distances that you're dropping the ball from. So you would drop the ball, plot several values of s and t squared for various heights you were dropping it from, and you should get a straight line with the gradient of g over 2. So just double your gradient to get a value for acceleration due to gravity. Question 4. The men's long jump at the London 2012 Olympic Games was won by the Great Britain and Northern Ireland athlete Greg Rutherford with a jump of 8.31 metres. Name the type of path that a long jumper will take when airborne. So this path that you take when you're in the air has a mathematical name, and it's a parabola. It's a parabolic path. State the horizontal and vertical velocities components of his initial velocity v if his launch angle was 37 degrees. So this is just finding components of v. So v has these horizontal and vertical components, and one of them is cos, v cos theta, and one of them is v sine theta, and it depends on whether these lines are opposite or adjacent to that 37 degrees. So you may remember that in maths you were taught this phrase SOHCAHTOA, where sine relates to the opposite over hypotenuse, cos relates to the adjacent over hypotenuse, and tan relates to the opposite over adjacent. So the one that's going to be sine will be the one that's opposite. The one that's going to be cos will be the one that's adjacent. Okay, so sine relates to the opposite. So we look and we see that this line is opposite to the 37 degrees, so it's v sine 37. This one here is adjacent next door to the 37 degrees, so it's going to be v cos 37. So our horizontal component here is going to be this v cos 37, and our vertical component is going to be this v sine 37. So part C1 says calculate the time for which he was in the air if the magnitude of his takeoff velocity v was 9.21 meters per second and his launch angle was still 37 degrees. So what we're going to do now is work out the vertical behavior of this, because it determines how long he was in the air for. And so we're particularly interested in this vertical component of velocity, because if we imagine something just sent straight up at that, that will give us the time that this object was in the air for. And if we go in particular to the halfway mark, then we reach a point where vertical velocity reaches a zero on its way up, and that will give us half the time of flight, which is the quickest way to do this. So we start by making a vertical UVAS list. We're starting at this value of v sine 37, which we now know that's 9.21 times sine 37. When he reaches the highest point, vertical velocity will go to 0. A is in the downward direction, which means it's negative at the value of g. S we're not really interested in, and t is an equation requirement. So we need some kind of UVAST equation that doesn't require us to know S, the vertical height that he goes to, but does contain t. And that particular one is v equals u plus at, and that means that v minus u over a will equal t. And we just need to fill that in to get the time to the halfway point. So t is going to then be 0 minus the original velocity of 9.21 sine 37 divided by minus 9.81. I'm making that 0.565 seconds to the halfway point, and so we get a value of 0.565 seconds, and t total is going to be 2 times t half, which is 2 times 0.565, which works out to be 1.13 seconds. Now, annoyingly, there is a real shortcut that doesn't involve him going up in the air like this. We do know how far he went, because that's in the question, and we do know his horizontal velocity. So there's a much simpler answer to this, where his 8.31 meters is divided by his horizontal velocity to get the same time. So probably a lot of this kind of question will involve the UVAST equations, but we could have easily taken a shortcut there. So part 2 here, calculate the magnitude and direction of his resultant velocity 0.5 seconds after takeoff. So that's going to be just before he reaches the halfway mark, so it'll still be pointing up slightly. There's some point just before he reaches the halfway where he has a velocity half a second in. So at t equal to 0.5 seconds, there will be a new velocity. Remember that the horizontal velocity stays constant the whole time, but he will still have a tiny bit of residual vertical velocity here, and that will give him an overall velocity, which is the sum of these two. So the horizontal part is going to remain at u cos 37. What we need and are interested in is this tiny vertical part. So we want to find the final vertical velocity at t equal to 0.5 seconds. So we still have an initial vertical velocity of 9.21 sine 37. V is the thing we're interested in. A is still g. S vertical is some value that we're not desperately interested in. And t we know to be 0.5 of a second. So we're not interested in the vertical height. We again need an equation that doesn't include s, and we've used that one before. So v equals u plus at, 9.21 sine 37 added to minus 9.81 times a half, and that gives us a v vertical of 0.64 meters per second. So we can now draw a triangle, or we can add to our triangle up here that this is 0.64 meters per second. So I've added that in here, and now we can get the details of this v, because it's going to be the square root from Pythagoras' theorem. It's going to be the square root of this squared plus this squared. So v is going to be the root of 9.21 cos 37 squared added to 0.64 squared, and then the root of that. And I'm making that about 7.38 meters per second. And the angle is going to come from taking the inverse tan of 0.64 over u cos theta. So theta is going to be tan to the minus 1 of 0.64 over 9.21 cos 37. Okay. Student states the principle of moments as when an object moves, the sum of the clockwise moments equals the sum of the anti-clockwise moments. Identify two omissions in the student's statement. Okay, firstly, it's not about when an object is moving. This happens when an object is in equilibrium, and in particular, rotational equilibrium. So when an object is in equilibrium, the sum of the clockwise moments equals the sum of the anti-clockwise moments. You also have to be specific and say that these moments have to be about the same point. Part B, the student attends a gym. He holds a 1.5 kilogram dumbbell in his hand and keeps his arm horizontal before lifting the mass upwards. The forearm pivots about the elbow joint and has a weight of 25 newtons, which acts 19 centimeters from this joint. The force in his bicep, FB, acts vertically upwards at a distance of 6.8 centimeters from his elbow joint. The center of gravity of the dumbbell is 37 centimeters from the elbow joint. The vertical force at the elbow joint is labelled FE. The situation is shown in the not to scale diagram. So we've got a joint location here, an upward force from this bicep muscle. This is a bicep muscle pulling upward here. We've got the weight of the bone and the arm, the whole forearm here, acting down. And we've got the weight of the dumbbell on the far side here, acting down. So we've got a downward moment caused by this, a clockwise moment caused by this, clockwise moment caused by the weight of his arm, an anti-clockwise moment caused by the bicep muscle. Part 1. Use the principle of moments to calculate the magnitude of the force in the bicep, FB. So, we've got a pivot problem here to deal with. The pivot is right at the left-hand end of the rod, so this rod represents the arm. So pivot at this end, we've got the weight acting down, we've got the weight of the arm acting down, and we've got the bicep pulling up. We know that when this is in equilibrium, the total anti-clockwise moment about this pivot will equal the total clockwise moment about this pivot. So we've got 25 newtons worth of arm, we've got a 1.5 kilograms mass, which will be 1.5 times g. We've got distances to these locations from the pivot, from the diagram. Those values are 19 centimeters and 37 centimeters. And we've got a distance out to this bicep force of 6.8 centimeters. So in our moments problem, we've got FB times 6.8, and that's equal to 25 times 19 plus 1.5 g times 37. So that's the moment of the bicep force, the moment here of the weight of his arm force times distance, and the moment of this weight, which is a force times a distance. And so anti-clockwise moments equal to clockwise moments, and we need to solve that now for FB, so we need to take the 6.8 to the other side to get FB. So we've got 25 times 19, 1.5 times 9.81 times 37 for the moment of the other one, and dividing now by 6.8. And I'm making that 150 newtons. State an expression for the vertical force at the elbow joint FE in terms of the other forces acting when the arm is held horizontal with the dumbbell in hand. Okay, now because the bicep is pulling up and these two are pulling down, then the elbow joint would also need to be pulling down, or rather pushing down. So these are all the forces marked on. And the total upward force should equal the total downward force. So FB should equal FE plus 25 plus 1.5. So FB upwards equals FE plus 25 plus 1.5 G. Getting FE on its own, we need to take FB and subtract the other two from it. So FE equals FB minus 25 minus 1.5 G. And determine the magnitude just means put some numbers into that. So FB is 150, and we're subtracting 25 and 1.5 times 9.81, which is 110.3 newtons. Question 6 then, part A, number 1. Define the Young's modulus of a material. Remember, Young's modulus is stress over strain, so we could define that as this ratio of the stress in the material to the strain of the material, where E is, sigma over epsilon, and you can define then the terms sigma and epsilon. So the SI for the Young's modulus is the Pascal. Express the Pascal in SI base units. So we think of like force over area, and force can be thought of as like mass times acceleration, and we're dividing by area, so we can now put units into all of that. We've got kilogram, meter per second squared, and divided by some more meters squared, and then cancelling we get kilogram. The top meter cancels with one of the bottom meters, so we get meter to the minus 1, and we still had a seconds to the minus 2 there. Part B then. The seat of a garden swing is uniform and has a mass of 1 kilogram. It is 0.4 meters long, made from a light but rigid material and suspended horizontally by two wires as shown in figure 6.1. One wire is made of nickel and has a diameter of 1.9 millimeters. The other is made of copper and each wire is 5 meters long. When a boy of mass 40 kilograms sits in the middle of the seat, it remains horizontal. So what they're basically saying by saying that it remains horizontal is that there is equal stretching of these two wires made of different material. So what you've got here is that where the Young modulus values are different, there has been some compensation in the diameter of the wires to give them the same extension as each other. Now he's in the middle, so the forces, the tensions on these two cables are going to be the same. Both cables stretch and both start out the same length, so the strains are going to be equal. The change in length over the original length for both of these is going to be the same because the extension is going to be the same and the original lengths are both the same. So they ask us to state the tension in each wire. So we recognize that we've got tensions pulling up and they're going to be equal, and we've got a downward force of 40 kilograms plus 1 kilogram, so it's like 41 kilograms times G downward, and we've got T and T upward because the kids in the middle, these T's are going to be even. So 2T equals 41G. Equilibrium, so 2T's pointing up equal 41G pointing down. And that means that T must be 41 times G over 2. And that works out about 201 newtons. So part 2, the stress in the nickel wire is 7.05 times 10 to the 7 pascals. Calculate the strain in the wire. So Young modulus is stress over strain. So we need to get the strain on its own. And that's going to be the stress over the Young's modulus for this material. So that's 7.05 times 10 to the 7 divided by 1.7 times 10 to the 11. And that gives 4.15 times 10 to the minus 4. And strain, remember, is a ratio, so it doesn't have units. Calculate the extension of the wire. Okay, so we have a strain value, and we know that strain is the fractional extension. And that can be written as epsilon equals delta L over L0. We have numbers for all these things, so the extension is going to be the strain times the original length, and so we just multiply that by the original length, which I think they said was 5 meters. And if we do that, we get 2.08 times 10 to the minus 3 meters, which is 2.08 millimeters. Now they're asking us to calculate the diameter of the copper wire. Now, because the seat remained horizontal, then both wires must extend by the same amount. So we know now the extension of the copper wire must also have been 2.08 millimeters. So we plug that into our equation. So our Young's modulus is stress over strain, where sigma is force over area and epsilon is delta L over L naught. And we sub those into that, and we get the L naught on the top with the force and the delta L on the bottom. And all we do now is put the area as the subject and take the Young's modulus, the big E, down. So we get that area is F L naught over Young modulus times delta L. So just identify some terms. F, this is the tension, this is the original length, this is the extension, and this is the Young's modulus for the copper. So we know all those. Might want to do a wee bit more simplification before we start plugging numbers in. Area is obviously pi r squared, which is pi like d over 2 all squared. So area is like pi times d squared over 4. So if I put that expression in over here, we can rearrange this now for d. If we take the 4 over and the pi over, d is going to be the root of what we've got. So the diameter is going to be the root of 4f L naught over pi times the Young's modulus times the extension. So the root of 4 times f, and that's the tension, we found that to be 201, times L naught, which was 5 meters. And on the bottom line, we've got pi times the Young's modulus for copper times the extension, and we need to make sure that we're consistent with our top line. Our top line had meters in it, so the bottom line needs to have meters in it. So we need to run that through the calculator now. And I'm getting this value in meters, which would be 2.29 millimeters. Okay, so I'm going to just upload this. This is mostly the forces stuff. The rest of the stuff are electrical. I'm going to upload those in a second video.